Here, welcome everybody. Here I'm gonna discuss something about Matlab coding, and this program is all about the projectile of delivery, right? You guys understand cricket, right? So whoever understand cricket or any form of game where a ball is delivered into the sky and it comes down in a projectile motion, right? So here's what I'm gonna do is to plot this projectile motion of delivery uh, in Matlab code. Here I use the ground based Matlab code because it can be applied into the other versions of coding like Java, Python, or C or anything like that. There is another tool actually to implement this, which is a simulation tool in Matlab, which is Simulink. But I won't show this in this version. I'm gonna show it in the later version because this is basically the ground-based coding system. So I'm gonna stick to that. And what I done first is to use the OpenGL function software, so to get the maximum resolution for graphics, and then I used a white background to green form to make the background green, right? And then I used another function which is view, and this view basically gives us the 3D view. Here the thing is -90 0 10, which means the X, Y, and Z position in the PC or in the monitor. The 0 in Y means it do not have any angle. It just gonna straight, and then -90 means from the opposite direction, 90 degrees. So it's gonna give a straight view, and 10 degree in Z means it's gonna give a view from 10 degree height, right? So basically I manipulated the Z axis, right? So that's about that. And then sorry about that. Well, then I use the manipulation of the axis, right? My axis is called axis x lim -330, y lim -1 to 4, and z lim 0 to 4. What I use here, x lim means the x axis would be from limited to -330, because the length of the page is basically 3.79 meters, so this is gonna cover that. And y lim is the width of the page, and which is 3.6 meters, so it's gonna cover that -1 to 4. And z lim is basically the height, so I thought that the height won't cross 4 meters, so I use this. And then I use this view again, right? And then I use the aspect to make the aspect ratio of x and y and z same. So that is basically that. And then I use hold on, and I draw the surface of the peach and the stamp and the bale, right? So I use the cylindrical function here that's built in Matlab, x cylinder, y cylinder, z cylinder, and that's about that. And then I use the surface function to imply this. See, this is basically stamps, right? Because the stamp has a height of 0.71 meter, and that's the other portion of it, x, y, z. That's how I thought that I would get the bit result in the graphics. So you can try the other versions, other ratios as well. So it's up to you. And then basically the length of the page is 23.78 meters. So this thing is basically for the bales. And then shading and lighting was added. And after that, that is the pitch. Here you can see, oh, the thing is going down barrel every time I say that. Yeah, as linspace is a vector form from -3 to 30, that's the value. So is basically the length of the page and y is basically the width of the page. And when I use the mesh grid, then it can create an area with that width and length, right? And then I add color into it, fiscalize color. Then I use cam light and axis tight. You're gonna understand the function of those. And then I basically draw the various lines in the page from there. Here it's gonna go very fast, so I gonna hold it for you to see. You understand when you do this. There's no need to explain this. Just a simple graphical portion of it. Well, that's where the graphical portion ended, right? Then I use the while loop. Here, why do I use the while loop? Because, well, I want to take the input automatically after simulation is ended. So I use the while loop, the never ended for loop. That's why I used it, and that's basically the x direction of the projectile. So 0 to 23.9, and then I use 5 inputs, right? The first one is polar side in feet, and the second one is initial speed in kilometer per hour. The third one is the vertical release angle or line length control in degree, and then this is basically the angle in radian. This is G, 9.8. You all know that, the gravitational coefficient, and that's speed in meter per second, right? 5 by 18, and then that's the height in meter. Well, that is converted from feet to meter, right? So I used to multiply 0.0348 because that's the conversion. And then I used another input which is the release position from the piece. That basically means the over the wicket or the round the wicket, the point of the pitch where the ball is delivered, right? And then the horizontal release angle with the pitch, that basically controls the in-swing and the outswing. Then what I did in the code is that well, the first I'm gonna show you is that is basically the projectile equation, which means x in tan theta minus gx squared divided by 2 cos square v square cos square to the right. And there is another constant added with that because the ball ain't been delivered from the ground position, right? It's been delivered from the hand of bowler. So that's basically the height of the hand of bowler, right? In meter. Here it's converted from feet in meter, right? So after that, when the delivery when the height of delivery is 0 or less than 0, right? Then with the normal projectile equation, the ball gonna go underground, but we cannot let that happen. It's gonna have to bounce from that. So I use the break to break this for loop, and I here use a flag, which is p, which takes the value of I, right? The counting number, how many times the for loop it's gonna go before the height of the delivery goes to 0, right? And then I use another flag which key which take the value of p, or basically the I, right? And this shows the value of qi. It doesn't have to do that, or for simulation reason you can do that to use the value in other positions. So if you do not want to do that, you just discard this portion. And then, well, I use two things. When the angle is less than 0, right? When angle is less than 0, b is the angle basically, right? Particle release angle, and that is the radian form. So when the angle is less than 0, then I use for loops, two for loops. The first for loop is j, which I will describe later. The second for loop is inside the for loop j. Here what I used x uh, in the bracket portion I minus q, right? So here I equal q plus 1 and q equal p. So I equal basically p plus 1 and q equal what, p. So x I p plus 1 minus q equal to p. So x equal p plus 1 minus p. So x equal 1. So it starts from the initial position, and as I equal q plus 1, then I starts from q plus 1 and q means p. So this for loop ended with p times, right? And then this for loop starts p plus 1. So initially the latter part of that. So it's a continuous process. We continue, and when I equal q plus 1 or p plus 1, then it goes to the initial position, because x equal x into that position means 1, and to bounce it from there I just revert the angle minus p, right? And the same case applies here. If z is less than 0, then break and do the same thing. So that's basically that, and I use this j because I don't know how many times the ball gonna bounce. So I use this function for loop to calculate the bounce before the ball reaches to the end of the length, so 23.78 meter. Until that the ball gonna bounce, and this gonna count this bounce. So that's basically that, and that y is another function to calculate the in-swing and outswing. That should be a straight line, right? So y equal to x tan theta plus c. C is the you can see the input. C is the release position from the piece. So what I used here is not a straight line. I used a parabolic aperture in this function. Is 0.4 x tan theta to the power 2.6. I used this value from curve fitting or from my previous experience, and plus c is the release position. So that's gonna control the in-swing and outswing, and also the position where the ball is released. And then for graphical portion in 3D animation, I used sphere. That's a built-in function, and this function is used for the length, width, and height of delivery, right? The diameter of delivery or the ball, cricket ball. So I use surface, and surface axis is manipulated by this sphere function. So here you can see that. So I then gonna just manipulate x sphere 0.05, that's the radius of delivery. Y sphere is same, z sphere is same. I use the same coefficient because well, x sphere means only 1 meter, right? So I use I used to multiply 0.05 to get 0.05 meter, and I use this to all axes because I want a symmetrical diameter, right? In both x and y and z directions. So I use this, and that's the face color and S color of it. And then I use AD transform. Here's something to be noted. Here my axis, I used it previously, and my axis is the parent of C, right? And C is the child of my axis. My axis I used first to limit x, y, and z. I'm gonna show you in a minute. Here my x is equal to x limb minus 330, y limb minus 1 to 4, z limb 0 to 4, right? So that's that. And then I have another thing to show. That's v on 0.95 into j into to the power 1.1 into v, j on into v, which means that when the ball bounces, it's gonna decrease the speed to 95%, right? That's why I use this after first bounce. Here's the portion I was talking about. First x on surface, and then C equal H transform parent my axis. So C is the children of my axis, right? child of my x, sorry, and then I use the set function to get the appropriate value. So C is the parent of S1, right? And then draw now, I use that function, and then x stack, and I use the similar thing here, right? So this one's for bail actually, uh, stamp and bail. So that's K3 parent F and X start. Oh, sorry. This is actually for the for the animation, right? This H transform parent my axis, and this is set K3 parent F. So F is a parent of K3 and my axis is a parent of F, right? So I use this for the motion of the ball. So I use a for loop, and then I use the translation equal make HT from translate xi y zi, which I get from the previous equations, and then set C equal matrix translation. When this function gonna calculate the translation of the delivery, right? And then I use false point 1 and then plot 3 xi yi zi d. This portion, this plot is gonna show the direction of the delivery in dot blue portion. So I gonna get a projectile or idea of projectile from this. So then I use draw now, and this some other portions you may not need to use this for any reason. I use this because I had an intention to develop this code further. So I'm gonna use rotation and another translation when the ball hits the distance, that but I don't gonna show this in this version. I'm gonna show it in the next version, right? And this is the special conditions for no ball, white ball, or if the ball hit the stamps, and you're gonna show out. Here I use display no ball. So when the condition of this gonna fulfill, then the legend gonna show the no ball, and then when this condition is fulfilled, it's gonna show white ball, or the ball hits the stamps, is gonna show out. This kind of things actually happened here. And when this other three things doesn't gonna happen, then it's gonna show legal delivery, right? That's basically the code, and then I gonna simulate this. Here's I gonna cross this, and first I use this. This is the bowler side 6 speed, and then initial is 145 km/h. Then vertical release angle -7 degrees, and then release position of the pitch I use 3. That's over the wicket delivery, so 3, and release angle I use 84 degree. That's basically the angle between x and y. So that's it doesn't work there, so I use another one, same values, and 3. The inside I'm saying is as the distance from the pitch. Sorry, that is 84. So that's basically the projectile of delivery. As you can see, it's out, right? And then the input gonna come automatically. I use another portion. I use the height and speed same, but the vertical release angle is also same. What I gonna change is the position of the delivery release from the pitch. So I gonna use a round wicket delivery to show. So I use that is 0 and that is 3.6, right? So I use 0.5. That gonna basically start from there, and then I use 94 degree actually. That's 94 degree. here as 94 degree from y-axis, right? So that's how the ball gonna get out swing and gonna hit the stem, right? So it's gonna show out, and then I'm gonna show a no ball. So height is same, speed is same, and what I'm gonna say, if the ball is thrown in the positive angle, then the ball gonna go high and it's gonna give a no ball. So I use 5 degree angle, positive 5 degree angle, and over the wicket delivery. So I use 3 meter, and vertical, or sorry, horizontal angle is 84 degrees. So the ball gonna go without any bounce and it's gonna cause a no ball, right? So it's a no ball, as you can see from the from there, from the legend. And then I'm gonna show a white ball. So that's the height, that's the initial speed, the vertical angle, well, I'm gonna use -7, and over the wicket, around the wicket, so I'm gonna use 3, and well, you're gonna use 94. So you see it gonna go out of the length or line, so it's gonna cause a white ball, right? So that's the white ball. And lastly, I'm gonna show a legal delivery. Those things doesn't gonna happen, then you're gonna show a legal delivery. So I use the height same, the initial speed same, the vertical release angle same, over the ground wicket, well, as 3, and the swing, for swing I use well, not 90, maybe 80, 86, right? 86-degree horizontal angle. So that's the legal delivery. So that's basically the end of this version. Thank you for watching. Good luck with your effort in next time, right? So practice this in your home, and it's a basically a very easy trick to practice. So well, this is a guideline. So thank you very much.